I'm Dr. Ron Eglin. This is EGN3443, Probability and Statistics for Engineers. And we're in Module 4, and we're starting to get into the probability distributions. And right now we're going to be talking about discrete probability distributions. Now, first thing we're going to talk about is the difference between discrete and continuous numbers. Continuous numbers, well, it's simple. Discrete, 1, 2, 3, 4, 5. Okay, that's, roll of a dice, flip of a coin. They've got discrete things. They're discrete events. Continuous numbers can go 1 point, well, I'll give you an example. Height. Height does have specific numbers depending upon the accuracy with which you're measuring it, but it's a continuous. There's an entire range of those. So that's continuous. All right, well, knowing that, we're going to talk about different discrete probability distributions and when you want to use them. All right, let's start with the concept of probability mass function, which is something that you just actually saw on the previous slide. That little dice thing was a probability mass function. It was actually the visualization of a probability mass function. So first, you got to understand what a random variable is. Okay, a random variable is something that's random. Okay, a function that is assigned numerical value to each possible outcome of a random experiment. Okay, so you've got things that are random. And you've got those things which actually fit a distribution so that they're predictable. Now, if you're talking about, let's say, one roll of a dice, you roll the thing and it can take the values of 1 to 6, and each one of them has the same value, same probability of actually it occurring. But when you say you're going to roll 10 dice and you're looking at the total, or because there's a lot of different ways to get to it, or you look at the actual individual values that go with it, or you roll a dice 10 times and you look at that, well, roll a dice 10 times, each one of them is going to have the same possibility of occurring, but they do fit patterns. And what we're really going to talk about is those patterns. So in the probability scale, 0 to 100%, 0 to 1, okay, you've got things that are impossible and you got things that will happen with 100% certainty. Well, very few things actually fit that, but you've got a scale in between all of those. So let's talk about a little bit about the probability mass function, and we're going to talk about two things. We're going to talk about the cumulative distribution, the cumulative probability distribution, and the probability mass function. Now, here we go. Visualization is key. So looking at the probability mass function of a binomial distribution, okay, and that's the example that I have here. We haven't talked about what a binomial distribution is, but we're going to talk about it in just a second, okay? Or the cumulative distribution with the probability mass function, which, by the way, these two plots, the first two plots, show the same thing. The third one doesn't show the same thing. It's actually a Poisson distribution. We're going to talk about when to use a Poisson distribution, too. Different distributions fit different specific scenarios. So we really want to actually decide which distribution fits the scenario that we're going to be talking about. So how do we do that? Well, let's go. One more thing that we're talking about is the concept of expected value. So let's say if you roll the dice a bunch of times and you wanted to know the actual average outcome, if you roll the dice thousands and thousands of times, the average outcome would be a 3.5. The dice goes from 1 to 6. So you basically, each of those have the same level of probability. So if you averaged out all the different things that occur, you'd have 3.5. And the expected value is a formula. Okay, and actually there's the notation for the expected, for the formula is right there. It's a summation of basically all the different potential outcomes here. But, and you can calculate this. This expected function in the dice example is right here. I wanted to point that out before we went on. You basically average out all the 1 through 6 because they all have the same probability, and that gives you that 3.5. All right, what does this really tell us? Well, this is just kind of groundwork for what we're going to do in just a minute. We're going to get there, don't fret. Now, the other thing that we want to talk about when we're talking about probability distributions is the variance that actually occurs. And there is a variance formula for that in the standard deviation, which is basically the square root of the variance. And what it does measure is the spread around a specific mean or an expected value. Now, in the dice example, with the range of values there, you kind of want to think that that's going to probably fit pretty linear. I mean, pretty constant. But it is something we want to look at. Now, one of the other things that we're going to talk about is residuals here. We're not going to get to it right now, but there is variance and standard deviation in these specific types of distributions that we're going to be talking about. So all that as groundwork, let's kind of slide that. We're going to come back to it later, and we're going to talk about the actual distributions because that's where we wanted to go. And we've already talked about variance and standard deviation and means and expected values. Now let's talk about the distributions. So the first one we're going to talk about is the simplest, the Bernoulli distribution. And it is really, really simple. Okay, you got a single trial with two possible outcomes. That's it. Okay, you have P or 1 minus P. Okay, probability P or probability of failure, which would be 1 and minus P, be the opposite of it. So some examples of this would be a coin flip, a yes, no question, pass, fail. This fits a lot of different things. Okay, there's a whole lot of things that do that. But in and of itself, it's relatively straightforward and simple that you deal with this Bernoulli distribution. Now, of course, there's more to it, but it's going to actually be a lot more useful when we move forward to the next one, which is the binomial distribution. Binomial distribution is tremendously useful in the probability. Now, if you only had n equals 1, the binomial distribution becomes a Bernoulli distribution. But the binomial distribution is looking at multiple independent trials. Okay, what does that actually mean? Well, if I roll a dice and roll it over and over and over and over and over again, and I want to know how many times a number comes up, or if I flip a coin and I want to be able to predict how many times a coin flip comes, if I want to predict specific successes of different things, I can use the binomial distribution to do that. Okay, so remember, it's still got to follow the rules. So you're still talking about a binary here, something that actually can occur or won't occur. So let's say we're looking at how many times, let's say we're looking at seven heads and 10 coin flips is a good example of a binomial distribution. So fit the rules. Okay, coin flips, binary, it can either be heads or tails. Okay, they're independent. Each coin flip should truly be independent of all the other coin flips. So it looks to me like it pretty much fits binomial. It's got the rules here. Now, what does it look like? What does the probability mass function look like for this? Well, if we did 10 coin flips and we actually said, okay, the expected values for a binomial distribution, because a coin flips would fit this binomial distribution, how many times would you expect, if you did 10, what would be the probability of 5 heads? Okay, well, that's this middle one here. But we're actually asking the question, what's the probability of getting 7 heads? So if you were actually going to do this, you could use the formula here. Now, one of the things I want to point out is that you can, if it's a simple calculation, just sit down and do the formula. But most of the time, when we're talking about how we're going to use this, you need to have true visualization of the actual distribution and what you're looking for within that distribution, which means that you're going to need to be doing some plotting, which means that you're probably going to go ahead and use Python because it's got good plotting libraries and gives you beautiful plots. These plots came from Python. I did them myself. And you might as well, while you're in Python, have Python do the calculations for you because it can actually do the binomial distribution with the parameters that you've got relatively easily. And you can get the values. Now, does that mean you're going to sit down and just chunk through and figure out Python code? It actually does not do that. You can go ahead and ask any AI to write Python code to do a binomial distribution. Now remember, you've got to know what distribution to ask it to do based on the situation that you have. To create a binomial distribution with these parameters and give you some visualizations using PyPlot and using NumPy, it is quite capable of doing that. Running that Python code, pulling out the results of the Python code, taking those and putting them into our reports. Because the bottom line is that you know what distribution to use and you know how to put it into something that somebody can use to make decisions. Or in this case, just to get an answer, what's the probability of 7 heads and 10 coin flips? Now, if you look at the probability, you can see that you probably can't read this, but it's 0.1172. Or in the cumulative probability distribution function, it's 0.9453. But if you add 0.9453 and you add 0.1172, you're gonna actually see, hey, it's they add to 1. Now, that's the binomial. Now, just remember the rules. It's the rules that are important. If you need to come back and actually, have some sort of little reminder for the rules that go with the distributions, do that. It's not that really big deal. Now, realize that the binomial distribution is used for all sorts of scenarios. The coin flip, well, I don't know how many people sit down and flip coins and try to fit it to a distribution, but in things like quality control and medical testing, quality control, you have something that either is going to pass the quality control or fail the quality control. Well, that's a binary. That's either one or the other. Medical testing, you test positive, you test negative. Those are real world applications of the binomial distribution. Okay, so it's useful in these scenarios. It's the same as doing the coin flips in the example that I just gave you. You can create a probability mass function. You can calculate if you have 20 trials or you have the specific probability from these number of trials, figure out what happens in other scenarios. Okay, you figure out what the parameters of the distribution are, and then you can use the distribution to be able to predict other types of values. That's that simple. Okay, it is that simple. Now, when we went back to the coin flip, you know that the probability of any individual coin flip going up heads or tails is pretty much 50. It is 50%. That doesn't mean the probability underneath quality control of the pass or the fail, or the medical testing, positive or negative, those won't necessarily be 50%, but they are binary. They're pass fail, so they will fit good old the binomial distribution. Now, we're going to go to the next distribution, which is a different one. The Poisson distribution. Now, I'm going to read it to you, and then I'm going to actually explain it to you. It models the number of events occurring in a fixed interval of time or space. The given in the Poisson distribution is the constant mean rate. Now, what does that mean? Well, here's a good example, and I'm going to actually show you how this example works. It's got its PMF formula. There's the probability mass function. You can easily look this up. It's available. You can use it to calculate. There's a lot of calculators online where you can just plug in the lambda and the k, and it's going to give you back the value. So it's not really that hard to do this. You can sit down and knock it out with a calculator. There's a whole lot of ways to do it. But again, in this class and in real scenarios, you're going to need to actually come up with the visualizations and write a report around how you're using the distribution. Now let's talk about an example. Suppose we got a call center and it averages, we've got statistics and we know that that call center averages 5 calls an hour. All right, you want to know the probability of getting exactly 3 calls in an hour. Now you can just plug those numbers into that probability mass function and voila, you got it 0.1403. The occurrence of individual events that happen randomly and independently. Now, let's look at that and actually look at that in terms of the PMF and the CDF. Okay, so and now we're actually looking at a Poisson distribution. I had showed the same Poisson distribution earlier, but okay, so now you're looking at it and you actually look at in the Poisson distribution in the PMF, you can see for each of the discrete events, 0, 1, 2, 3, 4, 5, all the way up to 15 calls in a specific hour, you can look at the probability of those actually occurring. Okay, well, great. That's pretty awesome, and it allows you to pick off 3. Well, all that's really doing is looking at the probability mass function and calculating each of those specific values for all of those different calls. And by the way, it doesn't go down to 0 at 15. It can continue on, but it's a pretty low number. And then the cumulative distribution function is simply, you start with the first bar, the second one is you add the second bar to the first bar, you add to the third. So it's a cumulative. The probabilities of each of those get added, and it's going to taper off at 1. Now, in the specific situation that I just gave you, it actually has some real meaning. So, like this last plot is call volume distribution. So we can say normal is 3 to 7, low is 0 to 2, very high is 11 plus. What that means is you have to use that for specific planning because these are random events that you would plan for in a call center to make sure that you could handle. And that's the Poisson. All right, the next one, the good old hypergeometric distribution. Now, this one, in the binomial distribution, each of those events was completely independent of the other events. You flip the coin, one coin flip does not affect the next coin flip. Okay, but in a hypergeometric distribution, you sample without replacement from a finite population. What does that actually mean? Well, here's a really good example of this that you'll totally understand. If you have a deck of cards and you pull a card out, and that card is something that you're looking for the probability of, and you don't put that card back in the deck, the next card that you pull out is affected by the fact that you pulled out a card before. You haven't replaced it, and the population is finite. Therefore, it fits the hypergeometric distribution. And once again, we've got a probability mass function formula. Okay, and that probability mass function formula, you can use that directly and calculate it. You can go online and find PMF calculators. You can do it with your calculator. And I'm going to say it one more time. You're going to be writing reports. You're going to decide what distribution to use. You're going to validate that. You're going to basically justify why you use the distribution based on the scenario that you're actually solving. All right, here's a good example. You got 100 items in a batch, and you find that 20 of those 100 items are defective. Okay, N and K. Now, you're going to pull 10 items from that batch. Okay, what's the probability that 3 of those are going to be defective? That fits a hypergeometric distribution. You're pulling things out without replacement. Because what you're not doing is you're not picking up one random item and then sticking it back in the batch. That makes no sense. And then picking out a second one randomly and putting it back in the batch. You're pulling out 10 items and you want to figure out how many what's the probability of 3 being defective. Or actually, if you look for the mean or the central portion of the central tendency of the distribution, you can say, well, what's the most likely scenario to actually occur? And we can actually see that if we visualize it. Now, hope you caught that. This isn't really, it really isn't that hard. So, from the visualizations of the specific scenario that I gave you, this is a hypergeometric probability mass function with n equals 100, k equals 20, pulling out 10, and looking for the probability of exactly 3. If you go back to the function, you'll actually see, oh, look, those are the parameters that you actually started with. There you go. All right, and so the probability of exactly 3 in this case is roughly 0.21, and 2 is the most likely, that's essentially the mean of the distribution, or basically the largest value in the distribution is the most likely thing to occur. Again, the cumulative distribution function, just add those pieces together. And you can also now look at a quality control decision matrix, which basically says we're going to define good, bad, poor, reject, excellent, and we're going to look at what number of values that you pull in the hypergeometric distribution give you each of those values. So what's the actual probability of it being good, with good being defined as 2 to 3 of failures. And if you look at this, it's 52.7, which is essentially what would happen if you added in your probability mass function the 2 and the 3. And excellent being 0 to 1, that would be adding the 0 and the 1. All right. Okay. Now, if you did different sample sizes, you can actually look at how this thing is going to actually work for different sample sizes. Okay. Again, visualization tools are key here. And actually, you can see these visualizations are tremendously useful, and that's why we do them. Now, if you look at how you compare the two, you got binomial versus hypergeometric. Well, it's just what we just talked about. sampling with replacement, sampling without replacement. Probability remains constant for each trial. Probability can change after each individual thing that you pull out. They're independent trials, they're dependent trials. Okay, you've got different parameters and there's different scenarios to which they actually apply. Again, what's critical here? You do not need to memorize those equations. But you do need to know what to use where. Okay, you've got great visualization tools. You've got the computer. You've got all ways to actually do the calculations. You need to know which calculation to actually do. All right, geometric distribution. This is just kind of a specific situation when you're dealing with the Bernoulli. So you define a success, and you're looking for the first success that occurs in a sequence of independent Bernoulli trials. And I think if you remember, the Bernoulli trials were flip something, something happens. Okay, independently. Okay, well, suppose success was you're expecting a heads when you're flipping a coin. Well, this would make a perfect sense. If you want to know what the geometric distribution is, and you want to know what's the number of trials until the first success in those trials, well, in the flipping of the coin, it's a 50% success on the first scenario. And then there's another 50, but it may be tails, 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 heads. Okay, that's your geometric. Okay, so I'm not going to give you a specific. I don't really have a lot of situations where you're going to do this, but it's actually some of the most fun things to do is if you know the free throw statistics for a basketball player, which is the example I gave you here, and you know what the statistics are, you can say, well, if he keeps shooting it until he gets a basket, how many shots should it really take? Or what's the probability of it taking him 7 shots to actually get a basket? Well, if their probability is high for any given basket, that shouldn't be too many, but it can be 7. It's a possibility, and it fits that specific probability mass function. I don't have any examples that I did for this one specifically for you. It's useful, but it's not one that I use a whole lot. All right, discrete uniform distribution. Now, the definition, and this is one you gotta have to think about, equal probability for each value in a finite set of possible values. Okay, this one is pretty straightforward because the classic example is the dice roll. Okay, every single possible thing that occurred, that every single number has the same probability of occurring. Okay, so it's a fun, and it's actually the very first one that I showed you in the very first slide was the discrete uniform distribution. And again, it has its own probability mass function. It's got its own expected value. Generating random numbers is really this one. And guess what else follows this distribution? The lottery. Okay, well, okay. Well, we hope the lottery does. Maybe it's not as random as we think it is, but we hope it is. So here's some of the distributions. You're going to be using a lot of distributions here. Now, I'm not going to go into it in depth. It's a theorem that basically says you get enough data, everything looks like a normal distribution. So that's why we put this. I put this one on this specific slide because it approximates the binomial if you get a large n. But the ones that you're going to use most of the time in the engineering world, Bernoulli, binomial, and Poisson. There may be specific scenarios to go into those other distributions. That's why I mention them. You should know they exist. But the reality is and the true reality is that a binomial and a Poisson, if you know when to apply those, you should be just fine for almost every scenario that you've got. And just realize that the Bernoulli is just a specific case of n equals 1 of the binomial distribution. Now, here's what you got to watch for. This is really important. First, know what distribution to use. I gave it to you clear. Make some simple notes to make sure that you know this. It's not that hard if you understand this. And if you know the basic rules of the distributions, you'll know which one to use. Knowing whether events are independent. Okay? The biggest mistake most people make is they use the binomial distribution essentially for everything when there is not independence amongst the trials, and they get bad results. Now, you can make computational errors. I don't expect you to make computational errors because you're not going to be plugging and chugging into a calculator. I don't want you to do that. You've got lots of resources available to you to use. You don't need to calculate. I mean, you don't need to memorize these probability mass functions. You need to know what the distributions are good for. And then the number one error a lot of times is you look at the results and then you just simply misinterpret them. And it's not hard to misinterpret the results, because one of the things that's like simple, if I go back to one of those examples that you had there, I asked you what was the probability of it getting exactly 3 calls in that hour, where I could have said getting up to 3 calls in that hour, which would be in a totally different result, because that would have been the solution of adding the, having 0, 1, 2, and 3 versus having exactly 3. And if you're rushing through this and you're just not paying attention, it's very easy to make that mistake. Don't make it. It's not that hard to not make that mistake. So you got the idea of what a probability mass function is. Those are those equations that you saw. You also saw how I can visualize those by plotting the probability mass function and also plotting the cumulative distribution function of those, making sure that you select the right distribution that you have there. In many situations, we're going to get a little bit more complex here. Those probabilities are, the probability of a die roll, the probability of selecting a card from 52, the probability of a coin flip, but sometimes those are actually have a little bit of uncertainty to go with them too. You should be able to get the calculation of an expected value from, especially if you know the parameters of the distribution. Knowing where to apply these, because reality is we're going to apply them to real world problems. I'm going to give you real world problems and you're going to pick out the right distribution to do, and then you're going to do some calculations, you're going to do some visualizations, and you're going to present results. Now, if you need to go back through those, I would just recommend you can get some nice little summaries. This is the discrete distributions. Next, we're going to cover continuous distributions because we're not done with distributions yet. Okay, but if you know those rules, you should be good to go. That's it. I know this is a long lecture, but you should be able to handle all this. That's it. Thanks. Signing out.